So I wanted to take a second and make a video here to help you with learning your amino acids. So again, I'd rather have you spend time learning things that maybe have future applications, or if you're learning a way to think about your amino acids, something that has future utility rather than just kind of trying to remember some esoteric sort of weird name or something that really doesn't have application to kind of future concepts in biochemistry. So again, when we have our amino acids here, amino acids are named amino acids because they have an amino group and a carboxylic acid group, and just reminding ourselves that we're going to have these protonation states. NH3 is going to be protonated here because the pKa of protonated amines being 9 to 10 is greater than physiological pH. The carboxylate group is going to be deprotonated because carboxylic acids having a pKa of around 3 to 5 is less than what we see for physiological pH, and so this is going to be the protonation state for these two groups. Remember that in the context of a protein, this is where coupling occurs, so this carboxylate group is going to be coupled with an adjacent amino group to make our peptide bond. So really in that case, when we have proteins, the only ionizable groups are going to be if we have side chains that have charges on them. So another way to kind of sort of help remember some things is I like to remember the numbers 9, 6, 3, and 2, or as we're going to talk about them in this video, 9, 6, 2, and 3. And those take this large group of 20 things and break them up into groups that are related. So 9 nonpolar amino acids, 6 polar amino acids. I'm going to talk about the 2 acidic amino acids first, and then our 3 basic amino acids. So hopefully kind of some strategies here, some stories that might help you kind of solidify your understanding of these names and one-letter codes for amino acids. So I'm going to start with the nonpolar side chains, and 9 of these amino acids have nonpolar side chains. And as we've talked about, and when we talk about protein structure, the driving force for formation of protein structure and for stability in proteins is the interaction of these nonpolar side chains within secondary structural elements. So the formation of tertiary structure is driven by these nonpolar side chains trying to minimize their contact with water. That is the hydrophobic effect. And that's how we're going to generate stability in protein structure. So when we think about these nonpolar side chains as a way to sort of start classifying them, the way I like to learn them and think about them is thinking about maybe how you learned organic hydrocarbons, right? The simplest organic hydrocarbon, right, has 1 carbon. Well, we're going to actually start with glycine that has no side chain, if you will. And so glycine is the simplest amino acid. So remember, at this alpha carbon here on our alpha amino acids, we're always going to have 1 hydrogen atom, and then we're going to have an R group. Well, if that R group happens to be a hydrogen atom like we see in glycine, then this group is going to be achiral. We're not going to have a chiral carbon here. Every other amino acid is going to be chiral. And one of the things that's important to remember is all naturally occurring amino acids, at least in our bodies, are going to be of the L configuration. So again, we talked a little bit about stereochemistry in class. If you need a refresher, make sure to go back and look at that handout that talks about the different kinds of stereochemistry. One of the things we'll see as we go through this series of nonpolar side chains is that a lot of these side chains are going to have the 1-letter code that's the same as the starting letter of the amino acid. And that's a reminder to us that in those cases where the starting letter is the letter that we see in the amino acid, and if there's another option, the letter that is the starting letter is given to the amino acid that has a greater natural prevalence. So this is sort of a reminder too that most of these amino acids are fairly prevalent in nature. And that's because these are the things that clump together to create that hydrophobic core in most globular protein structures. So if we sort of continue our trend here and say 0 carbon atoms, 1 carbon atom or a methyl group is going to give us alanine. And so again, the story that we talked about with alanine and having this methyl group is if people are doing sort of protein biochemistry and making some mutants of proteins, often what they'll do is what's called an alanine screen. And so by replacing any given amino acid with an alanine, you put in a methyl group there, so you don't kind of have this steric void. You have nothing in there, just an open space, but you eliminate functionality. So there's no relevant functional group there and just having a methyl group. So hopefully it's just a little bit of a story that helps you remember alanine. So we don't have a C2 version, we don't have an ethyl version in the next series, but we do move up to a propyl version. In this case, it's an isopropyl group in valine. And so maybe a way to help remember that valine is V beyond kind of having the letter here, but this has a, in terms of finding this structure, we've got almost the letter V here in our isopropyl group. So moving up from 3-carbon piece to 4-carbon piece, we actually have 2 flavors here, and they are isomers of one another. So we've got an isobutyl group and then a sec-butyl group. And yes, it would be nice if the isobutyl group went with isoleucine, but that's not the case. It's actually the opposite. But for both of these, their 1-letter codes are actually pretty easy to think about because they're the same as the starting letter for their name. So leucine and isoleucine are the 4-carbon side chains. So kind of shifting gears a little bit, we have proline, which is kind of a little bit of a strange looking amino acid, and that's because the backbone actually ties back and interacts with the amino group, and so our side chain is actually covalently connected to what will be the peptide backbone. We talked about proline quite a bit when we talked about collagen structure. Collagen is very glycine and proline rich, and that helps to favor the formation of those left-handed alpha helices that we need to see in that right-handed triple helix. That's collagen structure. So proline, again, hopefully an easy one to recognize. Side chain interacts with the backbone, so it's kind of a unique structure. Methionine, interesting one. It doesn't kind of follow our hydrocarbon series, but remember that ethers, and thus by proxy thioethers, are fairly nonpolar, so that's why it's grouped in this category. Methionine is one of these important amino acids because all proteins start with the codon AUG in the messenger RNA, and that codes for methionine. And so methionine is an important sulfur-containing amino acid. The next 2 kind of deviate from our, well, the single letter code doesn't match the starting letter of the protein, and these are 2 aromatic amino acids. So we've got tryptophan and then phenylalanine. So phenylalanine is pretty easy to remember because we just basically take alanine and we attach a phenyl group to it. So phenylalanine, and at least the 1-letter code is something that sounds like it's the start of it. Like if you were to spell phenylalanine wrong, you could at least spell it with an F. Tryptophan here, another aromatic amino acid, the only bicyclic aromatic amino acid that we have here. This amino acid is the same amino acids that's implicated in making you feel tired. For example, if you have a large protein meal like you would have like at Thanksgiving dinner. As a way to help me remember what the 1-letter code is, I'll say the word tryptophan, like TWYP, and that helps me remember that tryptophan is W. So almost halfway through in just thinking about our 9 nonpolar side chains. Moving forward to our polar side chains, I'm actually going to start with phenylalanine because we're actually going to bridge the gap between phenylalanine and our next amino acid because they're related to one another. So tyrosine here is a hydroxylated version of phenylalanine. We're actually going to spend a good bit of time talking about these 2 amino acids next semester in Biochem 2 when we understand protein metabolism. And phenylalanine is actually a prevalent amino acid in the artificial sweetener aspartame, which is found in NutraSweet. And some individuals have an inability to metabolize phenylalanine. It's a metabolic disorder called PKU, or phenylketonuria. And individuals who have that disorder have an inability to process phenylalanine, which means they also have an inability to effectively produce tyrosine. And tyrosine is an important precursor for skin pigmentation and melanin production. And so what we'll actually see is people who have PKU oftentimes tend to have lightly pigmented skin. Also, it's a situation where tyrosine is a precursor to certain important neurotransmitters. So all kind of information that we'll talk about next semester, but hopefully some stories here that help you maybe remember tyrosine. Tyrosine, another one of these, must not be a very prevalent amino acid because we can't use T, and so tyrosine is a Y. But I have tyrosine grouped here with the next 2 amino acids because of the functional group that's present, which is a hydroxyl group. So serine and threonine also have this hydroxyl group. And so serine kind of being the simplest hydroxyl-containing functional group on an amino acid with a hydroxymethyl group, and then a little bit larger with threonine, which has a chiral center here. But these 3 amino acids are important when we consider controlling and regulating the activity of proteins. So one of the important ways that we'll talk about as we move through the course here and that we regulate the activity of proteins is by decorating hydroxyl groups on proteins with phosphate groups. And so the hydroxyl groups on proteins come from tyrosine, serine, or threonine residues. And by putting a phosphate on these amino acids, that actually puts us into what we call a phospho state, which is more of a catabolic state, and then what we call kind of a need state. And then if we take our phosphates off and put ourselves in a dephospho state, that's more of a fed state. And so these three amino acids are going to be really important for that, especially serine and threonine. So as we move through the three other polar side chains, we can see that we've got cysteine here. We've spent a bit of time talking about cysteine. Cysteine, again, having this thiol functional group allows us to make some unique covalent bonds between side chains where we can form that disulfide bond with either an adjacent cysteine residue or maybe another molecule that has a thiol functional group. So in our insulin case study, we talked about the prevalence of cysteine residues in terms of keeping the A chain and the B chain together in insulin. We talked about cysteine in keratin structure and the importance of having those cysteine residues to impart either curliness or straightness to hair, and how hair chemistry can be modified using doing sulfur chemistry to either relax or perm hair. Moving through the next two that we have in our polar side chain category, they're actually related. The first one is called glutamine, and again, it has an amide functional group, and its sort of sister compound, asparagine. The only difference between these is one of them has one methylene group, another one has two methylene groups. How I like to remember which is asparagine comes first in the alphabet, so it has one methylene group. Glutamine has two. At the end of the day, and literally a month from now, whether you remember which one is which in terms of one or two methylene groups is not as important as that you remember that asparagine and glutamine have this amide functional group. And importantly, being able to recognize the one-letter codes so that when you see glutamine as a Q, you can see this functional group in the protein. So again, sometimes I'll say to myself, Q-tamine, and that reminds me that glutamine is the letter Q. And asparagine is, I'll hold that N at the end to remind myself that asparagine is the letter N. So I'm going to actually start the next series of two amino acids from asparagine and glutamine because they're related. So if we talk about asparagine, and if we were to think about hydrolyzing this amide, we'd end up with aspartic acid. So again, aspartic acid is the carboxylate version of asparagine. And related to that, glutamic acid is the hydrolyzed version of glutamine. Again, these are ones, the fact that these letters are not the first letters in the amino acids remind us that these probably aren't as prevalent as their sister compounds, so alanine here or glycine here. But again, if I remember aspartic acid, that can help me remember that aspartic acid is D, and glutamic acid, spelling the glue as Glue, like Elmer's glue, that can sort of help me remember. One other little thing I kind of wanted to highlight here about these two amino acids is sometimes you might see with a three-letter code either ASX or GLX. What that means is as they've isolated a protein and kind of subjected it to purification conditions, if you were to hydrolyze this amide in the presence of water, you'd get aspartic acid. So asparagine can be converted to aspartic acid in the presence of water. So when you have a protein that you're sequencing or trying to look at the structure of, you might not necessarily know, well, did this start out as an asparagine and then it got exposed to water and became aspartic acid, or was it always aspartic acid? So they'll often talk about these two residues sort of being interchangeable, and they'll label them as ASX or GLX. So one other thing to highlight is that when we're talking about having acidic amino acids, that means we're imparting negative charge to our protein in that area. And it's a little bit weird to think about that when you have something that's acidic. Normally you think about acidic and you think about protons and things like that, and you're like, oh, that sounds like it would be positively charged. But remember, things that are good acids actually give up their protons, and what we have left is the conjugate base that's negatively charged. So when we talk about maybe introducing mutations that would add negative charge to a protein, we're going to be wanting to put in our acidic amino acids here. The last one is to think about basic side chains. And just highlighting, when we think about something that's basic, we're thinking about something that actually would want to grab onto and hold onto a proton. And so these are going to be things that are positively charged, and they are going to be things that contain nitrogen, because remember, protonated amines having a pKa of 9 to 10 are going to retain that protonation state at physiological pH. So in retaining that protonation state at physiological pH, they will be positively charged. So we've got histidine here. Histidine is going to be a real important amino acid that we'll talk about both in lab and in lecture. In lab, when we purify our proteins have 6 histidines all in a row, which is kind of a unique feature. It's not something that's found in nature, so it provides a unique molecular handle for us to purify our proteins by column chromatography. How we're going to elute our proteins from those columns is we're going to use a molecule that looks like this portion, that looks like histidine right here, the side chain. It's called imidazole, and imidazole thus represents kind of free histidine. And so we can use that as a molecule to elute our protein off of our column. We're also going to see that histidine is one of those amino acids that actually has a pKa near neutrality. It's just above 6. And so that's going to be a really important thing for this amino acid to act as either a proton donor or a proton acceptor in amino acid active sites. So that's a really important kind of thing that we'll see multiple times with histidine residues. Arginine, again, another nitrogen-containing compound. This one's a little bit weird with 3 nitrogens here in what we call a guanidino group. And again, at the end of the day, I don't care if you remember exactly how long this linker is, but when we think about arginine, I want you to think about this 3 nitrogen guanidino group and something that's positively charged. So again, arginine, I like to think of it like a pirate, so you'd be like arginine, and that helps you remember that arginine is an R. Last amino acid that we have here is lysine. Make sure you don't mix this up with leucine. Spelling is important here, but that's sometimes too why the 1-letter codes are more important. Nothing special that I can help you with here to think about that lysine is K. That might just be one of those weird ones you have to memorize. But lysine has this very long arm with a positive charge on the end. We're going to see times where lysine is important in that regard, and having sort of the flexibility of this positively charged arm to do some unique chemistry. One of the things that's interesting that I like to think about with lysine is if you ever watch the movie Jurassic Park, or I don't even think it was necessarily part of the movie, but it was certainly part of the book, is they talked about when they made these dinosaurs, they actually made them be lysine deficient. And so they had to provide lysine in their diet in order to allow them to grow. And that sort of ensured that if the dinosaurs ever escaped off the island, that they wouldn't be able to survive because they had to have lysine supplied in their diet. So we'll talk a little bit more about stories like that later, but interesting aspect to think about that maybe helps you remember a little bit about lysine. So that's our 20 amino acids, and I hope this is something that helps you remember them.